Hi, I'm Carolina Nobre. This paper is work I did with Dylan Wootton, Lane Harrison, and Alexander Lex while I was a student at the University of Utah. Today I will talk about evaluating interactive multivariate network visualization techniques using a validated design and crowdsourcing approach. This work has two orthogonal contributions. First, we ran an evaluation on the pros and cons of interactive node link diagrams and adjacency matrices for visualizing multivariate networks. Second, we introduced a methodology for evaluating complex interactive techniques designed for experts in a crowdsourced environment. So let's get started. When we think about networks or graphs, we often think of its structure, or how things are connected. In the case of a social network, nodes represent people, and edges connect people who have some relationship to each other. However, real-world networks almost always have attributes associated to the nodes and edges. So in this case, we might have information on each person, such as their name, their age, and what they do for work. We can also have attributes on the edges, such as how do people know each other or how long they've known each other for. We can define a multivariate network as one where we have information about the structure of the network or its topology, as well as attributes of the nodes and edges. Our study compares the two most common forms of visualizing multivariate networks, the node link diagram and the adjacency matrix, whose interactive design you can see here. There are a series of works that compare node link and adjacency matrices, starting with a study in 2005 and a few follow-up studies that both replicate and extend on the tasks and network types. However, these studies only cover topology tasks and at most encoded topology-derived attributes such as clusters as colors on the node or node labels. What distinguishes our work here is that this is the first study to incorporate attributes, both in the visualization and in the tasks, when comparing these two graph representations. What this study aims to answer is, which of these techniques is better for performing different tasks with multivariate networks? In order to address this, we must first ask, can we even use empirical studies to evaluate these complex visualizations? If we consider the spectrum of visualizations that are amenable to empirical studies, it ranges from very controlled perceptual studies all the way to complex visualization systems. In the middle, we have studies using static visualization or controlled interactions. While the first three types are often used in empirical studies, complex visualization systems are very rare due to a series of challenges. The first and perhaps biggest challenge is how can we make sure that what we're testing is what we care about? When a participant does poorly on a task, was it because we didn't select the right colors? Or because we didn't use optimum encoding for the task? Or is it because the technique inherently does not support that task? To address this, we developed our designs by leveraging existing guidelines and knowledge on what the best encodings are for our tasks. For tasks where we only need to show two attributes, we use size for the quantitative attribute and color for the categorical one. For more attributes, we use nested bar charts, such as this one. The bars represent quantitative attributes, and small glyphs are used for categorical ones. Here's what a small network looks like with the nested bars encoding. We also consider edge attributes, where we use color to show the type of an edge, and width to show a quantitative attribute, such as how often that interaction has happened. Each visualization affords a certain set of interactions, such as dragging nodes or highlighting neighbors. In the node link diagram, searching for a node highlights the node in the graph. Users can toggle the highlight on and off by clicking on that node again. Highlighting a node also highlights all of its neighbors. Users can also drag nodes around the screen. Hovering over a node shows a tooltip with exact values for the encoded attributes. Let's move on to the adjacency matrix, which represents each node as both a row and a column in a matrix. An edge is a filled-in cell at the intersection of the source and target node. We use opacity to show quantitative edge attributes such as count, and color indicates the type of the edge. Quantitative node attributes are represented as bars in an adjacent table. We use colored binary squares for categorical node attributes. In the adjacency matrix, a node can be unselected by clicking on the intersection of its row and column. To highlight neighbors, users can simply click on the node column label. They can further group all neighbors by clicking on the sort icon under the column label. We then move on to the attributes in the table, including the ability to sort them by clicking on the column headers. Another approach we use to address the problem of confounders is validating our designs using external experts. We use heuristic evaluations with 69 questions asking for design suggestions and criticism, which we implemented in our final design. Another challenge with using crowdsourced empirical studies for complex interactive visualization is that we are using novice users who are not graph visualization experts. So the question is, can we train them enough to use these complex systems so that we can generalize the results to people who actually use multivariate network visualizations? What we found was a combination of both active and passive training can in fact give users the expertise necessary to complete these tasks. The average accuracy in this study was over 75%, with users who had never seen these multivariate graph representations before. The study had 4 sections and took participants on average 40 minutes to complete. The training component had both a passive and an active section. In passive training, a video introduced users to the network and to the visualization approach they had been assigned. In this example, the video is teaching the user what an adjacency matrix is. After the video, users engage in active training with a hands-on guided tour to learn how to interact with the visualization. Before starting the study, users had to answer 2 trial questions correctly. In order to understand the effect of extensive training for novice users, we ran multiple pilots and tracked detailed provenance. This allowed us to see things like how many incorrect answers is a user submitting before getting the trials right. Are they using all of the relevant interactions? Here we have an example of one of the participants where we can see how long they took on the training component and their timing throughout the study. We also had to consider how to best motivate our users to complete a study that took almost an hour. We did this by making tasks that apply to a relatable Twitter network and offering above-average compensation more than double what the average crowdsourced study usually pays. As a result, we recruited all participants for our study in just under 2 hours. Participants also reported that they found the study interesting compared to what they usually encounter. Let's take a look at how we designed the study itself. To run the study, we used a crowdsourcing platform called Prolific, on which we recruited 300 participants, 150 for each condition. We applied our study tasks to a Twitter network, which contains tweets during Euroviz 2019. We subsampled the original network to create a large variant with 75 nodes and a smaller network of 25. The study itself had 16 tasks, the first 15 of which were assigned in random order. The last task, shown here, was an open-ended exploration task where we asked users if there was anything interesting or particularly surprising about this network. The study had a between-subjects design, so half of our participants saw the adjacency matrix and the other half saw the node link diagram. We designed our tasks to explore several different hypotheses, such as the expectation that distractors, which are node attributes that are visualized but are not necessary to the task, will have a negative effect in terms of performance and time in the node link diagram. In the adjacency matrix, however, we expected accuracy and time to not be influenced by the number of distractors. For each task, we collected information on participants' accuracy, speed, as well as their confidence in their answer and the perceived difficulty of the task. We analyzed the results using bootstrapped confidence intervals and effect sizes, and also performed qualitative coding to extract insight types for each visualization. Our results both confirm previous work on studies that considered only the topology of the network, as well as found new differences that relate specifically to attributes. For example, similar to previous work, our results show that node link diagrams still outperform adjacency matrices for path-based tasks. For attribute-specific findings, we saw that when we included distractors, the adjacency matrix performed better than the node link diagram. This was true both in accuracy as well as in time. We also used our study to better understand the types of insights that each visualization naturally supports. The most common type of insight for the adjacency matrix were attribute overviews. These are those that give a summary of one or more attributes of the entire network. As an example, one participant noted that institutions have much fewer tweets in general than person accounts. The second most common insight type for the adjacency matrix were ranked attributes. In these insights, the ranking of one or more attributes is specifically mentioned, such as this participant who noted that one user has the second youngest account age and very few tweets, but still has the fourth largest follower count of the network. Insights for the node link diagram were mostly topology driven, meaning that they related to the structure of the network but did not mention any attributes. In this example, the user notices how several people only have one connection in the network and they are all with the same person. The second most common node link insight type includes information on the topology of the network as well as at least one attribute. This participant mentioned that they were surprised by the low attribute value of tweets considering how well connected certain people are in this network. Another common insight type with node link diagrams are those that relate to the comparisons of attributes within a single node. This participant notes that despite few tweets, this person had several followers and a long account age. Our study also has a few limitations. First off, our comparison of two complex systems make it impossible to identify individual factors that contribute to the performance of the techniques. For example, we do not know whether it is interactive sorting or the encoding in aligned bars that leads to attribute-related insights in the adjacency matrix. Another limitation is that we were not able to compare multiple different network types in terms of size and density. Instead, we focused on testing a broad set of tasks on networks with varying attribute configurations. As a result, we cannot make claims as to whether our results would generalize to networks with significantly different topological characteristics. To recap, this study makes two main contributions. We evaluate the performance of the two most common types of MV&V techniques and find that the adjacency matrix outperforms the node link diagram for clusters, as well as in situations where non-task essential attributes were encoded. Node link diagrams, however, are best suited for paths and tasks that rely on within-node attribute comparisons. We also contribute a new methodology for evaluating interactive techniques and highlight the importance of active training for novice users, as well as proper compensation to ensure users are motivated to properly complete longer studies. Ultimately, we believe that the view of the visualization community on which kinds of studies can be run on a crowdsourcing platform might be too narrow, and that a broader range of systems is amenable to crowdsourced experiments. Thank you for watching this talk, and we hope you'll check out the paper available along with all the supplementary material at this URL.